Hello, and welcome to the course CSE331 Automata and Computability. My name is Ajalanjum Islam, and for the next 12 weeks, my colleagues and I will try to guide you through what is one of the most fundamental and exciting branches of computer science. This lecture is going to be a very brief overview and introduction to the course, so let's begin. The theory of computation can loosely be divided into three major components. At first, we have automata theory, which is the study of conceptual machines, the machines that can imitate the thinking process of humans and can solve logical problems or computational problems. Then we have computability theory, which deals with the question whether or not a problem can actually be solved by a computer. And if a problem is solvable by a computer, we have complexity theory, which deals with the efficiency of the solution. The efficiency is measured in terms of time complexity, the time it takes to solve the problem, and memory complexity, which means the memory it takes to solve the problem. We also have formal language theory, which is very closely related to automata theory. In this course, we are going to focus primarily on the first two, that is automata theory and the formal language theory, basically the first portion. We will also take a look at computability theory, but complexity theory will not be a part of this course. So let's just take a moment to think about how human minds take decisions or how we think about something logically. Suppose when you see this sign, we know when we see this, given the input of the sign, we know that we have to stop now. Or when someone asks me a question like how many twos are there in this number, we know that we have to go through the individual digits and count the occurrences of the number 2. So in this case, now we know there are 3 occurrences of the number 2, so then we can send the asker an appropriate response. Or let's say we are trying to get to a certain destination, and if we are given the instructions as an input, we can then follow the instructions and then we can take decisions based on those instructions and reach our goal. So the automata theory basically started from this in the early 20th century, when mathematicians and logicians tried to develop the idea of a machine that can replicate this thought process the way we think. They wanted to develop the concept of a machine that can do the same. Automata are abstract models of machines that can, on its own, based on some predefined rules, perform logical functions on a given input. But not all problems are solvable in a computer, and that's where computability theory comes in, because it's also important to decide which problems can be approached from a computational point of view and which problems cannot be. A very famous example of not solvable problems is the halting problem. And the halting problem is basically the question if a system can be developed, which when we give the system a description or an algorithm of any computer program and its corresponding input, can the system decide whether or not the computer program will stop at some point or run indefinitely? Alan Turing proved that we cannot develop a machine that can simulate a system like this that will solve this problem. Anyway, so we have been talking about machines and abstract machines that can imitate the logical thought process of human mind, but how exactly is that done, or how can we achieve that? So I'm going to give you a couple of examples here. So first, just consider an obstacle avoiding robot. It runs on a very basic principle. If there is nothing blocking its path, it continues moving, and if there is an obstacle in its path, it stops. So how can I construct a machine that will implement this simple logical statement? So if we think about it, this robot can actually be in only 2 possible states. It can either be moving or it can either be stopped. So we have our 2 states here. And when it's moving, consider this, when it's moving, if it sees no obstacle in its path, it keeps moving, so the state doesn't change. But the moment the sensor picks up something blocking its path, it goes to the stop state, and as long as the obstacle is there, it remains in that state, and as soon as the path is clear, it goes back to the moving state. So there it is, a simple two-state machine that can simulate the logic of this robot. So let's take another example. Think of a vending machine. It has only two items. You can either choose chips or Pepsi. The way the machine works is that you first enter a coin and then press one of the two buttons. You either press chips or you press Pepsi. And after pressing the button, the machine gives you the food and it goes back to the original state. So anyway, what we have here is the initial state. The state where the machine is expecting any user to enter a coin. So if you enter a coin, it moves to the choice of food state. So in this state, you are allowed to give the machine choice. But before entering the coin, if you try to choose a food, that is, if you press the Pepsi or chips button, it gives you an error. Alright, so in the choice of food state, if you press Pepsi, it takes you to the Pepsi state. In this state, it gives you the product, that is Pepsi. Or if you choose chips, it gives you chips. But if you try to enter more coin without choosing your food, without pressing the buttons, it gives you more error. Similarly, in the Pepsi or chip state, in this state you are basically done paying and you have already chosen your product. So in this case, you are just supposed to take your product and leave. But if you try to enter more coin or press more buttons, it's gonna give you error. So this is another example where we are implementing a state machine that can simulate the logic of the simple vending machine that we talked about. So I hope you are getting some idea of how the things might work. So let's go back and take a look at the brief history. In 1936, Alan Turing first came up with the idea of an abstract machine that had, in theory, all the computational capability of a modern computer. Despite the massive capability of the machine, the idea of the machine itself is very simple. It only had a memory strip, an infinite strip of memory divided into cells, a read-write head that could either write into each cell or read from it, and a control table that would hold all the predefined rules that would tell the machine what to do in which situation. Alan Turing also tried to define the boundary between what a computer can and cannot do, which is, as we talked about, a part of the computability theory. These are some important milestones in the history of automata theory and theory of computation. If you want, you can pause the video here and read through it. I'm not going to read everything out loud, but there is something interesting to notice here. A lot of the pioneers in the field were actually from other genres. The first two persons to ever formalize a finite state machines were neuroscientists, and Noam Chomsky, who pioneered in the field of formal grammars, which is so very important in so many branches of computer science like automata, compilers, or natural language processing and text mining, actually had his background in linguistics and journalism. Anyway, let's look at some of the applications of automata theory. Finite automata and some formal grammars can help in the designing and planning and construction of many software components or many important systems. Also, the concept of computability can help us decide whether or not a problem is computable and whether or not to approach the problem directly. Because in some cases, when the problem is not computable, we can adopt workarounds like approximation or using some sort of heuristics to make the problem computable, and it is very helpful to know which problems should be approached directly and which should require some sort of workarounds. We are also gonna study the concepts of regular expression and regular language, which are widely used in pattern matching and pattern finding in many fields and many softwares. There are many more applications of automata theory. In fact, a renowned computer scientist, Stephen Wolfram, actually argues that eventually our entire universe might be described as a finite state machine with a finite number of different states and different rules. And anyway, so that's it for today. Until next time, thank you.